Example 138. When investigating the link between consuming canned foods and bisphenol A levels in people, researchers found that 26 subjects who ate a can of soup every day for 5 days had average BPA levels of 20.8 micrograms per liter of urine and a standard deviation of 3.1 micrograms per liter. For 27 subjects who ate fresh soup, their mean levels were 1.1 micrograms per liter of urine and a standard deviation of 0.5 micrograms per liter. At the 5% significance level, test the claim that consuming canned soup raises the concentration of BPA in urine. Assume BPA levels are normally distributed, and do not assume equal variance for the problem. Okay, so when I read the problem, I want to know if it's a hypothesis test or not. And when I look at this phrase, at the 5% significance level, test the claim, I can tell it's a hypothesis test. I can also tell by the way the problem is laid out that they're comparing two independent samples, one that has 26 people in it, another one with 27 people in it. So it's an independent t-test. I can see that because they're small sample sizes. So it's a t-test, not a z-test. They're independent samples, and we're running a hypothesis test. Okay, so once I recognize all that, my next step is to identify the claim in the problem, the claim. So it says here that test the claim that consuming canned soup raises the concentration of BPA in the urine. So this would mean that the mean for canned soup drinkers is greater than the mean for fresh soup drinkers. So C for canned, F for fresh is what I'm using. Let's get the null hypothesis and the alternative then. So when you look at this problem, you'll see that the claim here has got a greater than symbol. That's one of the symbols that HA uses. So we're going to go ahead and say the claim and HA are the same. Now, the opposite of greater than is less than or equal to, and that is the symbol we'll use for HO then. Okay, so now you have your claim and you have your competing pair of hypotheses. Our next step then is to find the data for the problem. Now, I use canned food here first, so I'm going to use the canned food data first, right? Keep in mind that you could have put the fresh first, and then it would have been the fresh is less than the canned, and that would only change some small details down the line. We can talk about that later, but the ultimate conclusion for the problem would be exactly the same, and so it doesn't actually matter which way you set that up. All right, but if you do choose to put cans first, then the canned data goes first down here. Now the N here is 26 for the canned group. The sample mean, the average level of BPA was 20.8 micrograms, and the standard deviation was 3.1 micrograms. All right, from there we had the fresh soup group, and the fresh soup group had 27 subjects. The sample mean was 1.1, quite low compared to the other group, 1.1 micrograms per liter, and then we have the standard deviation being 0.5. And you can see these are quite different from one another, which is probably why they asked us to not assume equal variances. Then we have finally the alpha level in the problem, that's 0.05 or 5%. All right, from here we're going to take that data and plug it into a test stat formula. Our test stat formula will be T, because it's small sample sizes, and the formula has the following structure here. We'll have the mean for the canned group minus the mean for the fresh group. Why canned and fresh? Because that's exactly how we set it up here, right? Canned and fresh, canned and fresh, canned and fresh. Be consistent throughout. Then we have the square root here. And the square root's nice and easy because we're not assuming equal variances. So we're simply going to have the standard deviation for the canned group squared over the sample size for the canned group, plus the standard deviation for the fresh group squared divided by the sample size for the fresh group. There's our formula. Now let's put our numbers in. Our numbers here are going to be 20.8 minus 1.1. Then the standard deviation becomes 3.1 squared divided by 26 plus this value here, which is 0.5 squared divided by 27. Let's work all that out in our calculator and see what we get. So if I put the top in parentheses, I'll have 20.8 minus 1.1, close it up, then divide by the square root of 3.1 squared divided by 26 plus 0.5 squared divided by 27. Close it up, hit enter, and we get a huge test statistic here. The answer is approximately 32.01. 32.01. This is a problem where you would not need to really do a critical value here because this test stat is so large, we have to be rejecting the null hypothesis in this case. But we're going to go ahead and get the critical value because it's, a skill set that we need to practice. So let's go ahead and work that out. Before we can do that, though, before we can get a critical value, we're going to have to figure out what the degrees of freedom is going to be for this critical value. So let's start by drawing the bell curve first. When you draw the bell curve here, we're going to look at the HA and determine what type of test it is. That's like a little arrow pointing to the right, so it's a right-tailed test, right? And we know that because alpha is 0.05, that's what's going to be the area in here, 0.05. So the area in the tail is 5%. Now all we need is the degrees of freedom, and we can go to the table and get the corresponding T alpha value. The problem is, though, is that the degrees of freedom is kind of tough here because we're not assuming equal variances, and the sample sizes are not the same. So if you remember, we had this horrible formula that we were working with when we did the confidence interval. We're going to use that formula one more time. So we need to come up with these quantities that we had in the formula. We need to have the A and the B, right? And then once we have the A and the B, we'll plug them into this formula. So let's take a little time to work that out here. We'll do this right below the test stat here. Okay, so what would the A be? Well, the A would be, in this case, the 3.1 squared divided by the sample size of 26. That's going to give us some number. Let's do the same for the B here. The B will be 0.5 squared divided by 27. And then let's work those out and get some decimal answers for those. So if I do 3.1 squared divided by 26, it gives me this long decimal answer. I'm going to store that in my calculator under the variable A. So you're going to get 0.3696, so on and so forth, right? And then for B, we'll have the same thing. It'll be 0.5 squared divided by 27. And we get 0.009259, so on and so forth, right? So that's enough for now. I'm going to store mine in the calculator as alpha B, so it's a variable B in my calculator. So I have these two stored in my calculator. Now I'm going to fill in this formula. If you don't have that store feature in your calculator, you'd have to write all these decimals down. Hopefully your professor does not do that to you on the exam. It gives you either nicer values to work with or provides the degrees of freedom for you. Or the whole point of the problem would be perhaps just that one step. That's a possible way to approach it as well. Okay, but either way, let's go ahead and do this problem then using this formula. So since I put everything in A and B in my calculator, it's going to be a little nicer to enter. So it'll be A plus B quantity squared divided by, put the denominator in parentheses, we'll have the A squared divided by its basically degrees of freedom, which is going to be 25 here, plus the B squared, so alpha B squared divided by its degrees of freedom. Since the sample size is 27, that'll be 26 for the B. Close it up, hit enter, and we get an answer of 26.25, etc., right? So the degrees of freedom here, let's remember that this will be T.05, and degrees of freedom will only be 26. It's going to be 26 because we truncate those decimal answers. So it's 26.25, etc. Truncate means we just remove the decimal portion, or in other words, you can think of it as rounding down. All right, now that we have that, let's go ahead and go to our table. Let's look up 0.05 and go down to 26 degrees of freedom on the T table. Okay, so we're looking for 0.05 and 26 degrees of freedom. So if we come over here to the 0.05 column and go down to where we see 26 degrees of freedom, we see that the value is 1.706. Okay, so we found the answer 1.706. That's our critical value, and then clearly this test stat of 32.01 is well within the rejection region. So because of that, we're going to conclude that yes, we should reject the null hypothesis, right? So we'll say, hey, let's reject the null hypothesis and therefore support the alternative hypothesis. And if you're doing that in this case, you're clearly saying, because the claim is the same as the alternative, you're saying that you support the claim. So we're going to say the sample data supports the claim. And so what does that mean, right? So the sample data supports the claim. And so what does that mean here? Well, it means that, in fact, eating canned soup does seem to increase the concentration of BPA in the urine over people who eat fresh soup. So fresh soup drinkers have a far smaller average amount of BPA in their urine, a statistically significant smaller amount. And because this test stat is so extreme, we would say that at any alpha level, we would find the same conclusion, right? 32 is just off the charts large. And so there's quite a big difference between people who are consuming canned soup on a regular basis versus people who are consuming fresh soup on a regular basis. All right, and that's it.